Okay, so let's talk about static and kinetic friction. We've talked about friction as being a force, and so that's familiar to you, but the difference now and what we're talking about is we're breaking friction into two different components, or two different types of friction. We're going to talk about static friction and kinetic friction. So take a minute and explain what could potentially happen when the man in the picture below walks down that slope. What do you anticipate happening? Right, bad things, okay. So my guess is you're probably thinking he's going to slide, he's going to fall, there's a caution sign for a slippery slope. So the question I want you to think about now is, why does this happen? If that essentially kind of looks like a block of ice, right, or something really smooth. So my guess is you probably have various ways to talk about it, but everybody is talking about the same thing when we're talking about this man sliding or slipping because of a lack of friction between his shoes and whatever this surface is. So here are the goals for this particular PowerPoint. We want to make sure that you understand the difference between static and kinetic friction, to know how to work with problems involving the effects of friction as well. So what's friction? Okay, we've talked about the fact that it's a force, right? By definition, friction is a force, but in particular, if we break it down a little more, it's a contact force that acts to oppose sliding motion between two surfaces. So when you think about friction, it's a contact force. That means the two surfaces have to be actually touching each other for it to be relevant or to be applicable, as opposed to field forces. And you know, field forces are things like gravity, nuclear forces, electromagnetism. So friction in particular is a contact force, and an important part of that is the opposing sliding motion part. So here's something that you know. Think about if you are walking across a carpet and you're scuffing your feet. The bottom of your shoe or the bottom of your sock, whatever you're wearing, is pretty rough, right? And so the friction that's happening between it and the carpet is going to be fairly high, which means it's going to be tougher to walk. But think about this. If you're in your house, let's say your house has hardwood floors, and you're in your socks, you can go flying across your hardwood floors in your socks because you have this really, really minimal friction that's happening. So the flip side of friction being high when surfaces are dry and rough is that friction is really low if the surfaces are wet and smooth, which should also make sense if you think about it. Think about people that are driving in the mornings, if you ride with your family or if you carpool to school. When it's wet and when it's rainy outside, people typically go a little bit slower. And think about that. There's a part of that that actually makes sense in terms of physics. When the roads are wet, there's going to be a little bit less friction between the car tire and the surface of the road, and so you're going to have a little less traction when you're thinking about stopping, starting, turning, making curves, things like that. So some factors that affect the amount of friction include the normal force. What do you know about normal force? You should be telling me right now that normal force means the force perpendicular to the surface, and typically the normal force is equal and opposite the gravitational force. And you know gravitational force is the force of gravity acting on an object's mass. The other piece about friction is that the materials from which the two surfaces are made, or the relative roughness of the two surfaces in contact, is going to control what the coefficient of that friction is. Now this is a new one, so you see you've got this coefficient of friction statement here, and there's this funky little letter here. That letter is a Greek letter, and it's pronounced mu. It's pronounced like if you'd spell it, it'd be M-E-W, but it's pronounced mu, and it is actually the coefficient of friction, and we're going to talk about what that means, but that letter is really important. So we've talked about the sigma is the net symbol, we've talked about theta, theta is the angle, mu is one we're going to use as well, mu is the coefficient of friction. Here's something that's important. The frictional force is independent of the contact area between the objects. That means if you think about this, when you have two large objects on top of each other, so let's say you have a gigantic box you're pushing across a carpet, the amount of friction that's happening between those two is independent of the surface area. So friction does not depend on surface area. Friction depends on other things, but not on surface area. And if you look back at the first two we talked about, we said normal force. Normal force is directly related to the weight. And then the second thing we talked about down here is the relative roughness of the surfaces, but it doesn't say anything about surface area. So two types of frictional forces that we're going to talk about, we're going to break these apart into static friction and kinetic friction. And I know when we talked about this back in class, a lot of you said, oh, okay, there's a part of that that makes sense. Static friction is the friction before things start moving, and kinetic is the friction after things start moving. So static friction, the force that keeps a stationary object at rest. So take something that's in front of you right now. Maybe you have your computer sitting on your kitchen table, and push it. Just try to push it. The amount of friction that's happening while you're trying to push your computer but it's not moving, the friction that's keeping you from even getting it in motion is called the static friction. It's the force that's going to keep things from starting to move. So if you had to define static friction, you could think about it as being the force that keeps things at rest at rest. And here's a graphic down below. You'll see a little bit of a free body diagram, and basically what I want you to think about, you see the sigma symbol here. So the net forces, or the sum of the forces, equals 0 in this case. And it equals 0 because if you look at the FA here, this is like me pushing a box. If this is my applied force, there's this static friction force acting opposite the direction I'm trying to push here. And the static friction force, when you look at it, is equal but opposite my applied friction. So that means I can push as hard as I want, unfortunately, until I get to a point where my applied force is greater than my static friction force, the box won't move. Now, here's an example of static friction. So here's what I want you to understand. To initiate motion, to make the box move, this guy has got to overcome the force of static friction. The friction doesn't go away once it starts to move, but it's no longer static friction. Now it's called kinetic friction. And if it's helpful, think about this. The direction that the static frictional force is going to work is along the contact surface, but opposite the direction of the applied force. So you see the guy is pulling, in this graphic, the guy is pulling to the right, so friction would have to be working to the left. Now, here's the part, this is the part where we start putting symbols to it. So static friction is shown by a lowercase f sub s. So basically this is what we use to represent the force of static friction. F for force, S for static friction. And the force of static friction is always going to be less than or equal to, and it's important that you're noting that this is an inequality, less than or equal to the normal force times this mu sub s, or the coefficient of static friction. So static friction is less than or equal to the normal force, which should be equal and opposite the weight in most cases, times the coefficient of static friction, whatever that number is. And mu sub s, again, coefficient of static friction. So here's an example. A 10-kilogram box is on a level floor, and the coefficient of static friction between the box and the floor is 0.5. What is the force required to make the box move? Now, I would say go ahead and give this one a shot. I don't have my bamboo here, so I'm not going to actually work this out. I'll come back and work these out later. But you should go back to the formula on the previous page. And the formula is the force of static friction is less than or equal to the normal force times the coefficient of static friction. Going, the amount of friction that there is between your car tires and the road or your driveway is static up until the point it starts to move. Now think about this. When your car starts to move, when you think about your tires, and when you think about the tires and you think about being in motion, if that's the case, here's what I want you to think about. Now that you're in motion, does friction go away? I hope you're saying no, right? It's not going away. It's still there. It may not be as great as it was before it started moving, but it's still there. If you have no friction between your tires and the road, that's hugely problematic at this point. And the force that slows a moving object down when the force of static friction has been overcome is kinetic friction. And this is the one that we've typically been talking about in class so far. We've been just calling it friction, but it's typically kinetic friction. An object in motion is going to stay in motion unless acted on by an unbalanced force. You're pushing a box, you give it one shove. If it's in motion, what's going to eventually slow it down is that kinetic friction. And here's another free body diagram to help make sense of this. So you have force of gravity coming down, normal force coming up, so there's force of gravity, normal force. This F is an applied force, and then the force of kinetic friction. Now remember, here's the interesting thing. These two are equal. That means the applied force that I'm pushing with is equal and opposite the kinetic force that's trying to slow it down. So since I'm in motion, I'm going to stay in motion at a constant velocity, because the sum of all my forces right now is 0 because my kinetic is equal to my applied. So if you're thinking about baseball, baseball is a great example of seeing kinetic friction. If you're sliding into a baseball player is going to come to a stop because of the force of kinetic friction. And the direction of kinetic friction, again, is always opposite the direction of motion of the object it acts on. Same as it is for static friction. So here's how we represent kinetic friction. F sub k is the F is for force, the K is a subscript that stands for kinetic friction, and F sub k is equal, this time instead of being an inequality, it's equal to the normal force times the coefficient of kinetic friction. The coefficient of kinetic friction is mu sub k. Again, this one's an equality, the other is an inequality. That's important. We're going to skip the examples. Here are some examples of coefficients of static and kinetic friction, and what's important is that you understand that the coefficients vary depending on what the particular materials are that we're working with. So rubber on glass has a much higher coefficient of static friction than something like steel on steel or ice on ice. And so it should make a little bit of sense to you. If you think about ice on ice, has almost no coefficient of static friction or kinetic friction, because that means that the surfaces are probably really, really smooth and or really, really wet. And think about these two compared to each other. Static friction is much bigger comparatively than kinetic friction for ice on ice. Ice on ice is 1/10 for static friction and 3/100 for kinetic friction. So static friction you're seeing across the board is higher than kinetic friction is. So some things about coefficients of static and kinetic friction. Values are going to depend on smoothness, temperature, and are approximate. Usually the coefficient is less than 1, but it's not always. And usually the coefficient of static friction is less than the coefficient of kinetic friction is less than the coefficient of static friction, but it's never going to be larger. So here's an inequality that represents that as well. The coefficients also depend on materials, but not on surface areas, contact pressure, etc. And coefficients of friction do not have a unit associated with it. It's just a specific number, okay? And the graph should show you, on the bottom, you see the static region for the first half-ish of the graph, and then you'll see a kinetic region. So these are representations of friction, right? And up here on the left, it shows you, if we're talking about friction in general, static friction increases as your applied force increases, and it's increasing to the point where your applied force is equal to your static friction, and at that point it overcomes the static friction and whatever you're pushing starts to move. So we talked earlier about pushing like your computer. You have to push for, especially if it's got the case on it, you have to push for a little while before it's actually going to start to move. It's an applied force the whole time, but the applied force initially is only equal to the static friction until you overcome it. Then you see this big drop. The big drop right here is that the friction now has turned into kinetic friction, so it's still trying to slow down the computer, but it's slowing it down at with a different force. So your frictional force is going to equal your applied force in magnitude until it reaches this point up here. That's the point where they're equal, and then it's going to drop down. That's where it's going to become a kinetic friction.